Hello, today we're doing hypothesis testing, chi-square. It's one of the first of three hypothesis testing that we'll be doing. So the other two are t-test and ANOVAs. Previously, we have done univariate analysis, which is the simplest form, described as a case in terms of a single variable. This has been like measures of central tendency, which is mean, median, and mode, or measures of dispersion, such as range, IQR, um, variance, and standard deviation. The analysis for univariate is very simple. It's only one variable, so it's only going to be like for gender, or for race, or for poll hit OK. Bivariate is what we're doing today. As subgroup comparisons describes a case of terms of two variables simultaneously. So for example, today we're going to do gender and poll hit OK, and race and poll hit OK. These are all two variables, and we can say just a lot more about them than our univariate. And then multivariate analysis is two or more variables simultaneously. This will happen at the end of the semester towards the last couple of weeks of April, where we do multiple regression and we learn how to interpret those regressions, and we have two or more variables all in the same equation, such as gender and race influence on poll hit OK. So as I said before, bivariate analysis is a statistical method designed to detect and describe the relationship between two variables. Chi-squares, t-tests, and ANOVAs are examples of bivariate analysis. Measures of an association such as lambda, gamma, and Pearson R are examples of bivariate analysis. And a tool or a technique is a cross-tabulation. So it's a technique for analyzing the relationship between two variables that have been organized in a table. So we've already done a couple of cross-tabulations where we looked at two variables and the percentages, and then we looked at two measures of two variables and the measure of association, and looked at the relationship between those two variables, whether there's an association or not. So cross-tabulations tabulate the number of times each possible combination of two variables values occur in a sample. To draw conclusions beyond the sample, researchers often employ a significance test based on the theoretical chi-square distribution. This is the only hypothesis testing that we do in this class that is not standardized. So chi-square depends on the size of the number and also the degrees of freedom that are indicated in the chi-square. It is chi-square, it's not chi-square. Chi is a T, chi is a statistical test. So the chi-square test of independence uses this theoretical distribution to evaluate a null hypothesis that in the population our categorical variables are independent of each other. A null hypothesis in this class is always going to be that there's no relationship between independent and dependent variable. A working hypothesis is going to be that there is a relationship between the independent and dependent variable. So we have this example of injury by skiing ability with column percentages, and you can see at the beginner level, no injury is 75%, and injury is 25%, and then as we move to the intermediate level, no injury is 90%, injury is 10%, and as we move to the advanced level of skiing, there's no injury 95% of the time, injury 5% of the time. So we would think from this table that seeing that 25% of beginner skiers are injured as compared to 10% of intermediates and 5% of advanced skiers, that there has to be a relationship. But this table doesn't demonstrate whether there's a statistically significant relationship or not. So what we're going to do is we're going to test it. The H sub 0 is the null hypothesis. In the population of all child skiers, ability and injury are unrelated, so there's no relationship between it. And in the population of all child skiers, ability and injury are related, so that there's not independence between the two. So that as you learn how to ski and become advanced, you're going to be injured less. So how we determine expected values by observed values. So expected values is what we would expect to happen, and that's based off of probability theories and specifically the multiplication rule. So that if the null hypothesis is supported, then the probability of the randomly selected young skier is both a beginner and uninjured should equal the probability of being a beginner times the probability of being uninjured. And so we've calculated below the probability of injured and uninjured. So 183 divided by the total, which is 214, and then 80 divided by 214, which is equal to 0.32. So that would be the expected probability of not having injury. And we take that number of 0.32 and we take it times 214 skiers. So the probability would be 68.4 of not being injured and being a beginner. So the null hypothesis again has no relationship between the independent and dependent variable. So the hypothesis of independence were supported. Then, according to the multiplication rule, the expected frequency, which is E, for any given cell in a cross tabulation should be E equals row times column divided by N, and this equation will appear on the final exam. So R stands for the number of cases in what that cell's row, C for the number of cases in that cell's column, and N is the number of cases in the table as a whole. So as you can see that we have 2 rows, 3 columns for degrees of freedom, and we apply the previous equation before where E equals R times C divided by N. So R in this case is 31 of injury times beginner, which is 80, divided by 214, which equals 11.6. So then in our observation, right, from this table, we see that 20 beginner skiers were injured. So is 20 different enough from 11.6 to be statistically significant? Well, percentage-wise, we would say, well, yeah, it looks like beginners are injured more often than intermediates, possibly. And then we would go from that. But we're more sophisticated than that, so we're going to determine how whether this is statistically significant or not by calculating chi-square. So chi-square, remember again, is testing on independent standard nominal variables and adding them together. We obtain a new type of theoretical distribution called the chi-square distribution. Again, this is not the only hypothesis test that's not standardized, so it doesn't necessarily follow a normal Bell distribution. It should follow a normal Bell distribution, but it doesn't necessarily have to follow that. And so for the next 2 tests after this one, there is a 5-step model that you will need to know for the final exam. And the first step is always making assumptions and meeting test requirements. So in the case of a chi-square, we make no assumptions about the shape of the sampling distribution. Remember, it doesn't necessarily have to be a bell curve. We think the model is independent random samples and the level of measurement is nominal. And step 2 is we're going to state our working and null hypothesis. So in this case, our null hypothesis is that there's no relationship between the independent and dependent variables, and our working hypothesis is that there is a relationship between the independent and dependent variables. So then in step 3, we select the sampling distribution and we establish the critical region. So in a chi-square, the chi-square is the sum of observed minus expected squared divided by the expected. In this class, we are always going to use a p-value or an alpha level of 0.05. We calculate the degrees of freedom as the row minus 1 times the column minus 1. And we looked up in the back of the book that the critical value could be, in this example, 5.991. So if you remember back to your stats class, a lot of times when you were calculating chi-squares, you would have to look at the back of the book and determine the degrees of freedom and the alpha level, and then you take your finger and you go down the column to find out what that critical number was. So where it says critical number 5.991, that is what it's referring to. So then step 4 is we compute the test statistic, and we have the chi-square obtained is the sum of the observed minus the expected divided by the expected, and the observed minus the expected squared. And for degrees of freedom, we take the number of rows minus 1 times the number of columns minus 1. So step 5, we start computing, and we are looking at, again, the example of skiing ability and with injury and no skiing, or skiing ability and injury. So as you can see, about halfway down the slide, we calculated the obtained chi-square is 11.87, and we determined the degrees of freedom is 2. So p-value of 0.0026. So in this class, any p-value that is below 0.05 is statistically significant. So from this calculation on the slide, you can see that we have determined that it's statistically significant looking at the p-values. If you look back to the table, right, they've done observed minus expected, and determine what numbers those are, like 1.03, 25, 43, etc. So all those numbers have already been calculated out for you in the table. Alright, so in step 5, we obtained 11.87, but our critical chi-square was 3.841. So, if the obtained chi-square is higher than the critical value, then you know it's statistically significant. So I want to spend a little bit of time talking about if your chi-square number or your t-test number or your ANOVA number is larger than the critical value, it is statistically significant. At the same time, a p-value is 0.05 or lower. So if you have 11.87 chi-square obtained, then your p-value is going to be below 0.05. So as your chi-square number goes up, or your t-test number goes up, or your ANOVA number goes up, then your p-values, probability values, goes down. So in this case, we can reject the null hypothesis, and we find support for our working hypothesis that level of skiers impacts injury or not. So we find a statistically significant relationship between skiing ability and injury. And we know this because the obtained chi-square is above 3.841, and the p-value was 0.002. Right? So it's below 0.05. So as the chi-square number or the test number goes up, your p-values are going to go down. So the limitations to chi-square is that if you have multiple categories such as social class, like you have lower class, middle class, upper class, elite class, etc., then you wouldn't want to use a chi-square. You want to use an ANOVA, which we'll get to later on in the class. If you have a small sample, usually less than 50, you can no longer assume a chi-square distribution applies. In most cases, if you have a small sample, less than 50, you are breaking stats rules and shouldn't be running any stats other than like percentages, measures of central tendencies, measured dispersion. If you have a large sample, you can reject the null hypothesis even though the relationship is not really supported, and you should have failed to reject the null hypothesis. For example, if you have 100,000 people in your sample, you may be able to show lots and lots of statistically significant results, and that is a factor of having 100,000 people in your sample. Thank you.